Good. Martin, you want to say anything before?
Okay. Oh, I'm just going to keep it short, Bill. Just say welcome to everyone for the last meetup of 2020, our favorite year yet. And I'm sure 2021 will be great, but it's a great way to end 2020 with thank Bill for doing this for us. But I don't think Bill Kennedy needs much introduction at all. So I'll leave it to you, Bill, to discuss the generics proposal. Over to you. Thank you very much.
Thank you. All right, I'm going to do all of this in 1 hour, and I'm just going to focus on generic functions today, and that will give us a good kind of understanding of where generics is going for Go. Now, before I share my screen, just a couple of things here. If you end up having any questions, just drop them on the chat window. I've got a second monitor, which I'm kind of looking at, which is what I'm about. And I can see that. I'll recognize that I see the question and I'll fit it in at some point as we go. And of course, you can ask questions at the end. Since this is a meetup group, not necessarily a corporate team, I do normally recommend that everybody have a conversation while I'm giving this talk. So, I mean, you can feel free to use the Zoom chat, or if you already have maybe a Slack channel on Gophers or something that you use, then use that. But it is nice when the group can kind of chat and discuss things as I go. Okay. Also, before I begin, let's just make it clear that the compiler has not been implemented. There's been no development work on the compiler as of yet for generics. They did start doing some preliminary work. And the word on the street is that in version 1.18, which would be released in February of 2021, no, 22, oops, 22. February 22, release 1.18, we could see our first version of generics in the compiler to use. Therefore, what I'm going to be working with tonight is the transpiler. That's the go-to-go tooling that they put out there so everyone could experiment and play with the syntax. And I just want to that no one is to use the transpiler for any production level code yet. So even if you're dying to start using generics, you can't use the transpiler, please, please, please. Plus the transpiler didn't fully implement the entire draft spec. So there are some things that are missing the compiler will have. Okay, I'm gonna go ahead and share my screen. I'm also gonna make sure I can see the chat window one more time. And we're going to get going here. Again, I've only got an hour, so I'm going to push hard. Now, I'm showing you the GitHub repo that I have for all of the generics examples that I've put together essentially, and the few that I will be showing tonight. I'm trying to paste that into the chat window, and I've just done that. All right, so that is the repo that we're going to be using tonight. Now you can see here that there are 13 examples. I don't have time to get through 13. I really only have time to get through 3 in an hour, which will be number 1, number 4, and number 5. So they focus on generic functions. 2 and 3 focus on generic types, and then the rest add a little bit more over time. But I'm gonna scroll down into the README real quick. You're gonna see a link right over here that says that can be found here. This is a link to the draft document. The draft document was updated last on November 25th. This draft document reads just like the Go specification. So if you're good at reading the Go spec, you'll be good at reading this document. If you're not great at reading the Go spec, like me, it took me years to learn how to read it, then you might see this a little bit. And part of this talk is so you don't necessarily feel like you have to read it or digest everything. I'm going to try to share with you a good amount of what the draft design is all about. Now, there's also a go-to-go link right over here. This opens up to a go-to-go playground. This is going to give you the ability to experiment and play with the new syntax. It uses the go-to-go transpiler. If you end up having questions that are code related, it may not be a bad idea to create a playground link and share that in the chat with me. Now, I'm not going to be using the playground. I'm going to be able to run the tool locally, and I'll show you that in a second. Now, I'm not going to take the time to read this. This is the high-level overview of what will be in the first release of generics in Go in that 1.18 February 22 release. I'm not going to read it. You can see that. I'm not going to be able to show you everything either in the next hour, but I'll show you out of it. So that's what you can expect to be in the release, and we'll talk about that. This is what's not going to be in the first release. Now, just because it's not in the first release doesn't mean that it may not eventually get into Go in a second, third, or fourth release of generics. We have to identify the need and the demand for these other things. This first release is going to be very, very targeted about making sure that we're happy with the syntax and certain things that I'll share with you throughout the talk that we're trying to solve day one. There are some blog posts about the code that I'm going to be sharing. I'm trying to write a blog post for every example. I haven't finished that. There's some other community posts. And then these are the instructions for downloading Go by the source code and getting the Go branch and building that tool out, which is what I've done already. So if I switch over to my terminal window, you'll see up here, I'm running a release from December 8th. And that's the version of Go that I'll be using. Not 1.15.6, but this one that has the Go tooling inside of it. Okay, brilliant. With all that being said and no other questions that I can see at this time, we're going to jump into the code. Now, what I want to do is focus on generic functions today. And I want to focus on this with an understanding of, one, how is generics going to improve our lives? And two, why we even need a new syntax to have generics. Remember, this is going to be in major version 1 of Go, not major version 2. Bill, when is version 2 going to come out? I don't expect to see a potential break in the language for at least another 3, 4, 5 years. Hopefully I'm retired by then, because I don't want to have to maintain 2 different pieces of content nor code bases, to be honest with you. So they're doing a really great job to make sure there's backwards compatibility here. And again, I think they're talking maybe by the time we get to a 1, 2, 3 in 3, 4, 5 years, whatever that ends up being. That being said, we're in a major version 1 here. Now, let's start off with this piece of code right here and kind of walk through that. I'm going to make it a little bit larger so we can all see it better. And we'll walk through this kind of experiment that I went through when I was first learning how generics were going to work in Go. So let's start here on line 13. On line 13, I've got a concrete function. I call it a concrete function because it's asking for data based on what it is. And in this particular case, that data is a slice of integers. And that's the only concrete data that we can pass to this function. Now, this particular function works with this collection of integers. And what it will do there is 5 lines of code. It will print a label. It will do a linear traversal using our language syntax and mechanics here with a for range, then print each individual integer and then a carriage return line feed. 5 lines of code. Now, I want to make a few bold statements about these 5 lines of code. The first one is I think that anyone who's written any sort of Go can highly read and comprehend these 5 lines of code. I think there's high levels of readability and code comprehension here. And it's due to the fact that we're using our language syntax and mechanics in this particular case, which we're able to do because we're dealing with concrete data. In fact, I'm going to actually take that to the next level. I think that anyone who's written code before, any software developer who's written code in a curly brace language, even if you've never seen Go, can read and comprehend the code that I'm presenting here. I think a lot of this is obvious. And that's why we love Go so much, right? You can come in and fairly quickly read and comprehend code and be fairly productive. And so here we are, 5 lines of code giving us our highest level of readability and code comprehension with this concrete function. Now, if I wanted to now display a collection of strings, at this point, I have to write a second concrete function. There it is on line 21 called print strings. This now only accepts a slice of string, and it is truly the same 5 lines of code. You can see that. The only thing that's changing are the labels and the variable names for the context. But there it is, right? And I'm going to make a point here that I love this second concrete function because if the first concrete function has that high level of readability and code comprehension, well, then the second function must have that as well. And isn't that what we're all striving for? I always want to write code to make sure that the average developer on my team can fully read and comprehend the code that I'm writing. And we're getting that. But what now if I want to write a print function for floats? and users and customers or any other sort of entity you can imagine. Eventually, as I end up with 3, 4, 5, 6 of these functions, I will be able to maintain my high level of readability and code comprehension. But what am I losing? I begin to lose my ability to maintain this code at a high level every time I've got to write a new concrete function for another type. And so I start to think about that problem because that's the problem in front of me. How do I maintain that high level of readability and code comprehension that's so important, but not lose my maintainability over time as the number of types that I want to be able to print here go up? And so I begin to start thinking about that. And I suddenly say, well, maybe this is a solution right here in Go 115 that I can use to solve my maintainability problem. And this function I'm calling print assert. And if you notice, it's using the empty interface, which means that it is not a concrete function, but it is a polymorphic function. This function is allowing me to pass concrete data, right, regardless of what the type is. And that's beautiful. That's what I need if I'm trying to generalize the problem away from 5 or 6 functions into one. But the problem is that when I pass that concrete data function using the empty interface, I know nothing about it. I don't even know what kind of behavior it can extend. And so what now happens is I need a way of inspecting at runtime what the concrete data actually is. Now, this particular function, in order to do inspection, is using a language mechanic that we call type assertions. In fact, it's using a generic type assertion. And what's happening here on this type assertion is that we're able to ask a question. And the question that we're asking is the concrete data that we passed and stored now inside of V, is that a slice of integers? We get to use the switch case to do that conditional logic. So if the concrete data we stored inside of V is a slice of int, we'll execute this code. If it's a slice of string, we'll execute this code. Now, at some level, I'm starting to feel a little bit better because instead of having 5 lines of code duplicate over and over, I only have maybe about 3 here. And now what I've kind of done is been able to consolidate at least the 2 functions I have right now into one. So that's kind of nice. I'm getting back some level of my maintainability. However, this isn't perfect, right? I mean, all I've really done, all I've done is consolidated those 2 functions into one. Now, it does give me my higher level of readability. We can read that. It has helped with maintainability, but this is not a generic function. And therefore, if I want to now display a slice of float and a slice of users and a slice of customers, I have more coding to do. And the other problem is at compile time, I can't validate that I'm actually passing a slice of anything in here. It's only a runtime check. So it's also quite possible that I could call this with a piece of data and not get any output at all. Now, before I move on with that question about code generation, I'm not a fan of code generation. I never have been. I don't think I ever will be. And code generation could be a solution for this, but not in my world. Some people have done that. Okay, let's move on. So I start to think about how all this really is a consolidation. It's helped a little bit with my maintainability, but what I really want is a generic function where I can do the printing that I want and only have a small code base to maintain. When I think about this for 115, another solution comes to mind. And that's the function I'm writing on line 56. I could use the reflect package. So what I've done now is I've written another polymorphic function using the empty interface so I can accept data of any type. There it is. Again, I'm blind to what that data is, but instead of using type assertions, I decide to use the reflect package. Now, if you notice here, I've got 8 lines of code I've written. So it's 3 more lines of code than I had to write before. But if you really stare at this code, I can't make the same bold statement I made earlier that anyone, even non-Go developers, can necessarily read this code and comprehend it, and that the code that's written here is obvious, because it's not. And the primary reason why it's not obvious is because we've walked away from our language syntax and mechanics, honestly. We're using an API. And if you don't know the API, then you really can't read this code quickly and comprehend what it's doing. I mean, I can break it down, right? We're going to call reflect.value of, which gives us a reflect value that lets us do some sort of inspection at runtime. We can validate whether the data that we passed in is a slice. If not, we return no output. Again, there's nothing we can do about that. We can't check that at compile time. We can't use a for range mechanic, but we can just use a traditional for loop, because we have a method named index that lets us do the linear traversal, getting back the concrete data and printing it, and then the label. So we are able to use the reflect package to write a single version of print, and I can print any collection that I want. But again, two problems, right? One, our readability is now diminished, even though our maintainability has gone up. And the reality is that we're still not able to, at compile time, validate. They're only passing in data that will pass the test on line 59. And so I've kind of flipped the scale. When we started this conversation, I had high levels of readability and these lower levels of maintainability over time. Now I've got this high level of maintainability, but my readability is now kind of fallen. And to be honest with you, I'm greedy. I want it all. I want that high level of readability and code comprehension with the high level of maintainability. And it seems right now in Go, I can't have both. I have to choose one over the other. And so what I want to stress here is that when I was getting that high level of readability, it had to do with the fact that I was working with concrete functions focused on concrete data. When I'm working on that concrete data, I'm able to use my language syntax and mechanics. When I was focusing on the maintainability, it had to do with that polymorphism, it had to do with the ability to write code that could work with data of any type. And so what's going to be nice here is that generics, and especially this first release of generics, is going to do that, just that. What the generic function is going to give us is the ability to write concrete functions that are polymorphic. And that's what's going to give us the big win here, the win of high levels of readability with high levels of maintainability. I just want to be clear here that our generic functions are what I like to think of as concrete polymorphic functions. We're going to explore that a little bit more. Now, with all that being said, I'm going to show you the version of the generic function that we're all excited to be able to have in version 1.18. Now, before I break this down, take a look at lines 82 through 86. I want you to notice that it is the same 5 lines of code we started with our concrete functions that were accepting a slice of int and a slice of string. We printed the label, we used our for range mechanics, we were able to display each individual value, and then we go ahead and we do the carriage return line feed. That code was our highest level of readability. But what's brilliant is I only need one version of this code for any given type, and now I've got my high level of maintainability. Now, to break down what's happening here, I'm going to remove the new syntax. And what I want to do is try to understand why we need a new syntax at all. Why would I need any new syntax at all? And mainly it's because we do have a backwards compatibility promise that we have to maintain. Look, I've removed the new pieces of syntax because if you're a Go developer and have been for a little bit, you can read this function right now. Your brain is wired to read this. And because we're human, you know what I'm really trying to do here. I'm trying to tell a compiler that this function print accepts a slice of T, but not really T. A slice of some type T to be determined later. That is really what I want to describe to the compiler. That T is not a real type, but a type to be determined later that represents a concrete type, right? And the problem is with the syntax that you see before you, right now the compiler assumes something like this. The compiler assumes that T is going to be declared by someone within the scope of the package that this print function exists in. And that's just not the case. We don't want to declare T ahead of time. We want T to be determined later and substituted for some type. Now, that's the problem. We can't just say T here. That won't work. So what we do is we need a new syntax to be able to tell the compiler, I see your question there, give me a second, to be able to tell the compiler that T represents a generic type to be determined later. Now, let me share with you, after many, many years of trying to figure out what is the best new syntax, okay, what we've come up with. So what we're doing now is we've decided that we're going to use a set of square brackets after the function name and before the parameter list. And within the scope of those square brackets, that is where we're going to define or declare the set of generic types that will be used with this function. We're not going to be able to use reserved words here because you may need multiple generic types, and you need the ability to name these types whatever you feel helps with the highest level of readability possible. Maybe you want to call this kite with a capital K or lower k. I do have some examples that say result, and you may want to do that. Now, I'm going to be using single letters for these collections because there's just a programming history or idiom behind that in other languages. But I want you to know that what we're going to do is define a list of generic types for this generic function. And we're going to do that inside the square brackets placed exactly where I'm showing you. Now, there's another problem. At first glance, this is how we handle arrays. And one of the things that are critically important is that the compiler speed doesn't get diminished and that the compiler stays as simple as possible. And so what we don't want is this syntax here in this place to be confused with some sort of array syntax. And we don't want to have to do extra passes in the compiler because that will slow things down. So what has been decided is that for every generic type that is declared, what must also be declared with it is any sort of constraint that needs to be applied to the generic type. In other words, in this case, we need a constraint, except right now T doesn't need to be constrained because there's no reason why T can't be anything. And that's the constraint we're going to use when there really is no constraint, any. Now, any is a pre-declared identifier, and it is aliased to the empty interface. However, don't get too excited about that. You're not going to be able to use the pre-declared identifier anywhere else in your code but right here. So don't think you're going to start replacing empty interfaces with this new identifier any. Not going to work. Compiler will not accept it. Now, before I move on here, is it possible to use this on custom types or will only be used for the built-in one? Let me keep moving forward, Dragon. We'll see where I get to. Okay, so we now understand why we need a new syntax, because we have to tell the compiler that T is not a concrete type that will be declared at some point, but T represents a generic type that will be substituted later for some concrete type. And then we have the constraint of any, which says that T can be anything. There we are. There we go. Okay, I want to see how this function works. And so what we're going to do is construct a couple of collections. There it is. I keep doing this. I don't know what's happening here. Let's start here. We're going to introduce a couple of collections. Here we are. Slice of int and a slice of string, and pass those collections to the appropriate functions, remembering that this is our concrete function, this is that consolidation function, and these two are our generic functions that we can use here in bold. So let's go ahead and move over to our terminal window and see. Now remember, we don't have a compiler implementation of this yet. So what we're going to do is use the transpiler. And I'm going to use that transpiler locally on my machine. And to access the transpiler, I'm going to say that we're going to use the Go tool, go to go. We're going to run this code, and I'm going to give it the code that's in the O1 folder. And sure enough, we transpile it, we build it, and then we run it. And there it is. I've got a generic function, a function that's applying concrete polymorphism right here, all right, to be able to execute the slice of int or strings right here. Now, the whole big deal is this, right? The big deal is we've got our high level of readability and our maintainability because I can do the following, right? We can go ahead and construct that slice of floats. There we are. And then I don't have to write any more code to use our reflect version or our generic function version. I can do that. We can come back up here. And now we're seeing floating points. Like that's the big win here, right? Well, one of the big wins. We've got that high level readability. We've got our maintainability. I don't have to write any more code. And off we are to the races with this kind of code here. Now, one other thing here that's important. I keep saying that this generic type that we're declaring here, which can be anything, is going to be determined later. Let's talk about what I mean about determined later, because there's really two types or two kinds of later in question. Now, when I say to be determined later, I could be saying at compile time, which is exactly what's happening here. If you notice, when I call print with a slice of int or print with a slice of string, the compiler here is supporting the call because it can infer, based on the fact that I'm passing a slice of integers, that t must be an int. The ability to infer the type is a critical part of this implementation because it allows, in this case, the function to look like any regular function call. So in this case, when we say to be determined later, we're saying at compile time. Now, this is only possible because the generic type t is being used as part of the data input, which means that we'll have information that we can use to determine what t is at compile time. But there may be times where the compiler cannot infer the type at compile time. So what do we do then, since t has to be determined later? In those cases, at the call site, we're going to have to provide the type information. And that's how you do it. It looks like you're just passing parameters again, but the parameters are type information. In this case, t, to be determined later, is being determined at the call site. And this code will run just as well as the other code that I ran before. Now, why could it be? Maybe t isn't being used as a data input. Maybe it's being used on the return. Maybe it's being used somewhere else inside the implementation, and there's nothing for the compiler to be able to leverage to be able to infer the type. In this particular case, however, we are okay. We can infer the type because it is part of the data input. Okay, brilliant. We now have seen our first generic function. We now understand the syntax and the need for backwards compatibility. We understand that these generic functions are really concrete functions where the generic types are going to be substituted later, sometimes at compile time, sometimes at the call site. We always talk also about how these generic concrete functions are also polymorphic, and I want to explore that piece a little bit more as well. But let's focus for a second on the idea of constraint, because that's really what we have enough time to finish or talk about for the rest of this talk. I'm kind of getting lucky right now that print has no sort of constraint that would need to exist on T, that the code, the 5 lines of code I've written here between lines 82 and 86 can work with any type of data. But the reality is that there are two different kinds of constraints that might exist or come up as you're writing generic functions. One of them will be based on behavior. There may be times where a value of that sum type T might need a method set of behavior that is required by the implementation of the function. And that's the first thing that I'm going to show you right now. So let's go ahead and look at example number 4. And I'm going to start this example out with some concrete types. So there on line 13, I'm defining a type named user, and user has a method named string that returns a string. And what that method does is it stringifies a user using that JSON syntax that I've hard coded. Customer again has a method named string right there in line 27. And that method also is using a JSON format to stringify a customer. That could be any format we want. The implementation of string for a user or customer is independent and separate from each other, even though they kind of look and feel a little bit the same. Now, to make the example a little bit more interesting, I've written these functions called stringify users and stringify customers. As we know, they are concrete functions because they accept data based on what it is. And in the first function, that can only be a slice of user. And in the second, only a slice of customer. But the idea is to range over that collection of user or customers, call the string method to stringify each individual user or customer and return the stringification back out. And you can see that in these 5 lines of code. So we use make to construct a slice of the right length for the return. We used our language syntax and mechanics to do the linear traversal. We can because we're working with concrete data. And then using append to the return slice, we call the string method against user and we're stringifying. And on line 49, we call the string method against customer to stringify. And once again, it's the same 5 lines of code, whether we're stringifying users or customers. The only thing we're changing are variable names because of context. And we don't have time for this, but we've already kind of went through this mental exercise, right? I could try to consolidate these 2 functions to try to maintain the high levels of readability while gaining back some maintainability. I don't think it's working here because there's a lot more code I have to copy. And so I think the use of the type assertion with our polymorphic function using the empty interface kind of breaks down here. So the next question is, well, can I write a generic function today using the reflect package then? Look, here is 13 lines of code that give us that stringification functionality in a generic way. Again, with some of the same shortcomings that we had before. It's polymorphic function. We're using the empty interface to accept that data. And then we're going to reflect over it again. We're going to validate that it's a slice. If not, there's no output. So there's a flaw. Again, we got to check at runtime. But because of the method set of len and index and some other things, we can write the rest of the logic. Let's construct a slice of the right length for the return. We can't use for range, but we can iterate over I over length. And this is kind of cool. I can inspect at runtime. Remember, before we were able to check at compile time. I can't anymore. I can check at runtime whether or not a value of any value that we're iterating over has a string method. And if it doesn't, well, there's no output. But if there does, we get to call it. And then we can apply that back to append. Interesting, isn't it? I do have 13 lines of code. Maybe we can argue that I've got higher levels of maintainability here now because these are the only 13 lines of code I ever have to maintain. However, our readability has truly fallen off the cliff. And even though I've written this code, it is hard to look at in one shot and read and comprehend what is going on. So once again, can our new generic functions that are going to work with concrete data, but still have that polymorphism, be able to give us back our readability while now maintaining or having that maintainability? I don't know. Let's take a look at what the generic version of this function could look like. And I'm going to pull out the new parts of it again, just so we can kind of look at it with our current eyes that know how to look at Go. So you should notice once again that the generic function looks almost identical to the original concrete functions. It's the same 5 lines of code using the same built-in functions and the same language syntax and mechanics, which gives us that high level of readability. But again, we're not asking for value or a slice of some type T, or type T itself, but of some type T to be determined later, which now we know means that T is a generic type, and therefore we're going to need to set those square brackets up and declare that T as a generic type. And by the way, as I'm working with generics, I always do this. I write the function first as if T is a real type, a real concrete type. And then I go, oh, no. T is really a generic type to be determined later. It helps me quite a bit. Okay, now what I want to do is run this code the way it is. I have a main function that will pass a slice of users and customers to this. But let's go ahead and transpile, build, and run example number 4. Now we get a compiler message here. And the compiler message says that there's a method call named string that is undefined for values of this some type T. In other words, the compiler is very confused because we are saying that a value of some type T to be determined later will have a method named string. Okay. Let me break something down for you before we get back to this. As I've already discussed, I can write a concrete function that looks like this. And we know at compile time that user has a string method. We see it in the declaration of user. This is a concrete function. It only knows how to work with values of type user, and it knows that we can execute string behavior. Now, technically, I could also write a traditional polymorphic function as well. This would work as well. This on line 111 being our concrete function, on line 115 being our polymorphic function. In this case, stringer, which is defined in the func package, defines a method set of behavior that requires the use of a method named string. In other words, this function here on line 115 can accept any type of concrete data as long as it implements the full method set of behavior defined by stringer, which is string. Now I keep calling this a polymorphic function, and it's because of this definition of polymorphism. Polymorphism means that a piece of code changes its behavior depending upon the concrete data it is operating on. Polymorphism means that a piece of code changes its behavior depending upon the concrete data it is operating on. Isn't it true that line 116 changes its behavior depending upon the concrete data it is operating on? It is absolutely true. We don't know what that behavior is going to be until runtime, because I can pass a user value through, and then we're stringifying users. I can pass a customer value through, and now we're stringifying customers. The behavior of the code on line 116 changes depending upon the concrete data we pass in, and that is only determined at runtime. Therefore, I call this our traditional polymorphic function. But as I already said to you, our generic functions are polymorphic as well. However, they're concrete polymorphic functions. How can I say that and why? Let's come back to our generic function. There is a call to string here being executed against the value of some type T. That right there is polymorphic because the behavior of that method call will change depending upon the concrete data that we're operating on based on what we substitute T to be. However, this isn't going to be determined at runtime. It's going to be determined at compile time, because at compile time, we're going to do substitution of T. Do you see how this really is a concrete polymorphic function? And there's the problem. There's the problem right there. We are trying to execute a method where that any constraint isn't enough, where the any constraint isn't valid because it can't be of any type. It can only be of types whose values know how to string. Interesting. Now, I brought this code back up because I wanted to share something else with you. Go back to your traditional polymorphic function for a second. Isn't it true, based on everything we just said, that an interface actually applies a constraint on the type of data that we can pass into this function? Sure does. Interfaces are technically ways of declaring behavioral constraint against the input, in this case of Bill, a already declared behavioral constraint. And if we get back to our generic function, isn't the problem that we need to provide a behavioral constraint that satisfies the idea that the data knows how to string? Yeah, that's exactly what's happening. And what's brilliant then is we don't have to need or develop any new syntax, since the interface is already giving us a mechanic to apply behavioral constraint. And that's exactly what we have here on line 114. I should be able to replace any with func.stringer. And that tells the compiler, look, T can't be anything. It can only be of type whose value implements the stringer interface. And now by applying the stringer constraint, the message goes away. Now you might think, Bill, come on, why do we even have to do that? Can't the compiler figure out that T has to implement the quote unquote stringer interface, or at least have this method? I'm sure that the compiler can be written looking at the call site on whether or not this is possible, except again, compiler performance and keeping the compiler as simple as possible is such an important part of Go that we don't want to do things that are going to slow that down. And so I don't think it's asking very much, considering we already have to do this with our traditional runtime polymorphic functions, to do it with our compile time concrete generic functions. I don't think that there's a big lift here for these types of polymorphic functions to define the interface there. But I wanted you to understand what was happening here. And now you can see it. Okay, we've got like 10 minutes left. And I do have to share with you the last constraint here that is actually something new that we've got to provide some new syntax for. Now there's a question here, if you don't have to return the specific type, would you prefer to write? We'll talk about that in a little bit. Now, let me show you a piece of code that presents a new problem that we don't have any real solution for today in Go 1.15. And I'm gonna make the code a little bit bigger. And I'm going to remove the parts of that code that are specific right now to generics. And I want you to look at line 16, and I want you to use your, you know what I'm trying to do on 16, right? You know what I'm trying to do. I want to write a function named add, which takes a value of some type T to be determined later, and a second value of some type T to be determined later, and adds those two values up and returns a value of that same type T. I want to write a generic add function. Now, here's the problem. I'm not using a method set here. I'm using the plus operator. Well, why is that a problem? Well, if T is substituted for an int, there is no problem. If T is substituted for a string, there is no problem. If T is substituted for a struct type named user, now we have a problem. Not all types that could be substituted for T can be used in a plus operation. In fact, I can also kind of share with you, even if we were using strings, subtraction is no longer at play. And so what we have here is a special constraint that's not based on behavior, but it's based on this sort of operation. I like to call this an operational constraint. And we have no way of describing this constraint today in Go. So look, I could do T, and I could use any right now because we need a constraint, but any isn't going to work because I just proved to you that T can't be anything. So how do we solve this problem? Well, let me show you what was the final result of years of debate, trial, and error. And there it is. Now, a couple things here. I want you to note that we're still using interface types to declare constraints. I like this. I didn't want a new keyword for this that would make interfaces and whatever this new thing is kind of difficult to wrap my head around. So since an interface already defines a constraint, I feel that using the interface again is perfect. However, remember, this isn't a constraint of behavior. It's a constraint of operation. And so the idea is this: leverage the interface, but declare the set of types that the generic function will and can only accept. And in this case, that type list string and all the instant floats would be what we're limiting the ability to call this function with. And we now, compiler can easily check that that type list is supported with the plus operator. Now, what's nice about this being or using the built-in types, which is going to hopefully answer one of the other questions that I saw here as we were going, is that the built-in types are universal to all packages, which means that no one would be restricted to calling add in this particular case against these particular types. And what's also nice is the compiler can leverage underlying type information. So if I defined a type named Bill, which was based on a string as the underlying type, I could also use Bill in calling the add function, because the underlying type can be matched. However, if I do something like this, now only Bill can be passed into add. Now that's kind of a major restriction, because we're only talking about Bill declared within the namespace of the package that all this is declared in. And it makes add very, very restrictive, right? Where what's nice about our polymorphic runtime functions, the interface, is that anybody can declare a concrete type in any package that satisfies the interface. Provides a lot of flexibility in the language. And here now, what I'm saying is that you can only use add with Bill and only Bill. Okay, kind of restrictive. But when we're working with the Go's built-in types, then it's a little bit more generalized. Now, here's something else that's kind of a bummer, but I think it makes sense, right? You can't use interfaces that have a type list as a traditional polymorphic function, because there's no method set, and our traditional polymorphic functions require the idea of method. I will only accept concrete data that implements the full method set of behavior defined by add only. Well, there isn't any. Huh? And remember, these are concrete types. Remember, our generic functions are about T being substituted for a concrete type. And so none of this really makes sense at all. And so we're going to end up potentially with interfaces that can't be used in a traditional way. Okay, just some potential shortcomings there. But trust me, after years and months of discussion, this is what has kind of surfaced as a best solution to solve this constraint. That's where we're at. Okay, a couple other things here. One idea to kind of help some of this is for the language to pre-declare some type constraints. And to experiment with this, the language or the Go-to-Go tooling, okay, provided a pre-declared type constraint called comparable, with the idea that T can be substituted for any sort of type that can be used in some sort of comparison operation like this if statement right here. That's really nice. And it's quite possible that we can end up with a bunch of these pre-declared type constraints. Like I could imagine addable for the cases where we're going to do adds, or subtractable or divisible. And then if you've got adds and subtractions happening, right, you could always use composition to create some larger interfaces, right, to support multiple sorts of operations, and when nothing would stop you. Though you can only have one constraint type per generic type at a time. So the idea is you could potentially do things like this, right? And you could have all the operations you need composed into one interface. All right. The other idea also is that maybe there ends up being a new package in the standard library with a bunch of these interfaces that everybody was going to have to, at some point, declare themselves. And so the standard library provides them, which again is nice because then they kind of become universal. Okay. So at that point, I think I'm going to end the talk here. There's more interesting things in this example, but we're really at the top of the hour here. And I'm going to leave that as an exercise for you to look at. So I'm off of my sharing. Let me just double check any other questions here. If you don't have to return the specific type, would you prefer to write? Yeah, so let me talk to that a second here. I'm going to say two more things to you before I kind of open it up to other questions. And I think that will answer some other questions you have. The reason in every example that I gave you tonight, okay, what I was trying to accomplish was, is there a way to get a good balance between readability and maintainability? I tried to show that when we're working with concrete data, when we're using concrete functions, our readability can be high because we're using our language syntax and mechanics, but our maintainability can drop when we have to perform that operation against multiple types because we got to write a new function every time. I tried to show how reflection gives us the ability to write generic code today and potentially gives us back the maintainability because there's one set of code. But you have to really understand the reflect package in order to be able to have that same readability and code comprehension. And plus all of the checks are at runtime. And so we could introduce bugs into production that the compiler would have been able to find if we were able to use it. And so I think what's nice is that the generic function, since it's really a concrete function that gives us polymorphism, can sometimes help us with the balance. Now, I love the reflect package. When it comes to data validation and marshaling, it's not going to go away. I'm going to use it. That's the right tool. But the question then becomes, when will a generic function be the right tool? And when will a traditional polymorphic function be the right tool? I would say this. I would say that if you can define an interface with a method set, right, then use a traditional polymorphic function. That's going to be more precise, and it's going to give you, I think, better readability and code comprehension and maintainability. However, if you have code today that is using the empty interface because you can't define a method set of behavior, if you've got code today that's using the empty interface as a return type, as an input parameter, where you're not doing data validation or marshaling, then I think the use of a generic function there is going to be the win. It's when I need polymorphism and I can't define that method set of behavior because one doesn't really exist. Now, where are there examples of that? Well, I'll give you a classic example. Go open up the sync package and look at the implementation of sync.map. It is an amazing piece of code because the developer or developers who wrote that focused heavily on cache coherency issues with the hardware. However, because it needs to be a generic map, it uses the empty interface, which is a real bummer because now we have type assertions everywhere as we pull data out of the map. Well, guess what? Isn't that a classic example for using generic types, where now I can have a sync.map that uses a concrete type that cleans up a lot of the code I need to write, and I gain all the beautiful work they did in the cache coherency problems that they solved? Absolutely. And so I think we're going to be able to see places in the standard library like sync.map will take huge advantage of this, where the empty interface is our only solution. I think we'll be able to see better data structures in packages in the standard library. And I think we're going to be able to see some concurrency packages in the standard library. And I think there's a lot of bugs in code today because everybody's rolling their own fan-ins and fan-outs and pooling patterns. And that stuff could easily now be implemented when we have generic types. And so I think I want you to look at your code. And I think I want you to ask, can I define an interface here with a well-defined method set of behavior? Even if it's just one method, that's fine. Then let's use a traditional polymorphic function. And when I can't, you have this new tool in the box. Now, let's talk about performance. Will generic functions make my code faster? I'm going to say the answer to that right now is undetermined, but I expect the answer to that to be no. I expect that a generic function won't perform any differently than our traditional polymorphic functions. And the reason for that is I'm expecting the language team to choose to use the same mechanics they're using today to write the built-in functions. If you think about it, the built-in functions are already generic functions in Go. The append function can take a slice of some type and a value of the same type and perform that operation. Same make, len, cap, copy, delete. They're all generic functions. The language team has had generics for a decade. It's just we haven't had it. And so I think what will happen is that they'll use those same generic mechanics that they have today to write the generic functions that we're going to declare, which means that they're not necessarily going to perform any better. And to be honest with you, that's what I want, because I don't want a single person in the Go on the planet choosing to use a generic function because it's going to be faster than using an interface. That's not the right engineering decision to be making. The right engineering decision always has to be the balance between code readability and comprehension and maintainability for the average developer on our teams. Okay, that's the end of my talk. I think I've answered every question that I saw. If I didn't, pop that question back up there, and or if somebody's comfortable letting go of their mic, Martin, I'm good with hearing any questions and or comments as well.
Great stuff. Thanks a million, Bill. Does anyone get any other questions or things they want to discuss with Bill now? Don't be shy.
That's okay. We got a football game to get to, you know.
Oh, yeah. Yeah, I think that was very cool. Bill, thank you very much for doing that.
Yeah, that was really, really good, Bill. Thank you very much. I've got one horrible question, and I don't know whether or not we'd even want this, but we're just in C# and stuff like that. I had this ability. Will we put in like a method into the reflect package to determine whether or not a struct is generic or not, so you could potentially call a generic function via reflect? Is that a terrible idea?
Well, remember that your generic functions won't be methods necessarily. So reflect is going to work. Reflect has to fully work. That's other work that they have to do. Now, if we had time, I can show you interfaces that declare a method set of behavior using a generic type, right? And that code would have to be generated for the substitution of T, and reflect would have to support that.
Sure.
There will be full support in the reflect package for generic types and those methods using generic types. That's absolutely for sure. That's why this is going to take a full year to implement, between the ability to infer, reflect, and some of the other work that they have to do and prototype and test.
Yeah, fair enough. Supposed to be the same for the AST package and everything as well, you know.
Yeah, all that's going to have to be there because that tooling can't break.
Yeah, cool.
Absolutely right. Yeah, it's on their radar.
Nice.
Cool. Anyone else got any questions? Comments?
No, it's all good.
No, looks like you've
shy bunch.
No. All good. You know, we're coming up to a break now. Everybody's ready to to grab a beer and enjoy the holiday. So I hope everybody has a great holiday, and I really appreciate it. And by the way, if you have any questions that pop up at all, now or later, here's my email address. Don't hesitate to send me an email with that question or code sample. If I can't answer it, I'll find somebody who can. However, there's a great channel in Gopher Slack called Generics, and there are people smarter than me who know a lot more. So that's also a great place to go.
Cool.
No, that was really good, Phil. Thank you for translating that spec into something that I can understand. That's great.
All right.
Brilliant. Thank you. Thanks for meeting, Bill. Thanks for agreeing to have a chat to talk this today. It's really appreciated. Thank you.
All right. Happy holidays, everybody.
Great stuff. Yeah.